Good evening. In today's lecture, we'll continue with chemical bonding. Till now, in chemical bonding revision, we have done basically sigma bonds, pi bonds. Basically, you can say it is valence bond theory, VSEPR theory, hybridization, and it is bond parameter including bond length, bond energy, and bond angle. And in the last class, we have just finished dipole moment. Today's lecture will revise resonance and molecular orbital theory. And this is going to be your last lecture, probably for related to chemical bonding chapter. So as per resonance is concerned, you can say in the case of resonance, it is relatively bigger term. You will learn resonance in more detail in another chapter, general organic chemistry. So resonance. In resonance, you can say for few molecule or ions, more than one Lewis structures are required to explain its all properties. For few molecule or ions, more than one Lewis structures are required to explain its all properties. These different structures are known as resonating structures or resonating contributor. These different structures are known as resonating structure or resonating contributor. These structures are hypothetical. These structures are hypothetical and do not exist. These structures are hypothetical and do not exist. Actual structure is resonance hybrid. The structures are hypothetical and do not exist. The actual structure is resonance hybrid, and it can show properties of all the resonating structures. It can show properties of all the resonating structures. So for few molecule, more than one Lewis structures are required to explain its all properties. These different structures are known as resonating structure or resonating contributor. these structures are hypothetical and do not exist. The actual structure is resonance hybrid, and it can show properties of all resonating structures. I can just take one of the example related to this to show you what is the meaning of resonance and resonating structure or resonating contributor. So if you see one of the example based on, let's say, resonance related to resonating structure, resonating contributor. So it is something, let's say you can just try to imagine that you are trying to describe to a friend what is rhinoceros look like. You might tell your friend that a rhinoceros look like a cross between unicorn and dragon. So a rhinoceros can show properties of both unicorn and dragon, but unicorn and dragon does not exist actually. So unicorn and dragon does not exist. They are just like a resonating contributor, resonating structure. They are just a hypothetical creature. They are not in equilibrium. The rhinoceros does not jump back and forth between two resonating contributors. Looking like a unicorn 1 minute and dragon in the next minute. So only rhinoceros is real. Dragon and unicorn are just a resonating contributor. So rhinoceros is something you can imagine. It is similar to resonance hybrid structure. So only resonance hybrid structure actually exists, and other structures are just imaginary structures. For example, in the case of, you can imagine benzene. For example, let's say in benzene, it's one of the resonating structure of benzene is like this, and the another resonating structure of benzene may be something like this. In actual structure of benzene, nowhere we have carbon-carbon double bond and carbon-carbon single bond. So in the case of benzene, you can just try to imagine everywhere we have certain single bond and double bond character, and you can represent this resonance hybrid structure of benzene as this. So these two are resonating structure of benzene, and this may be, resonance hybrid structure of benzene. So in the case of hybrid structure of benzene, it is somewhere, it can show properties of both resonating structure. And in this case, the carbon-carbon bond is somewhere between single bond as well as double bond. It can show properties of, so the carbon-carbon bond in benzene, it is somewhere between single bond and double bond. So if you see, as per, one of the compound, it is cyclohexane. It may be cyclohexene, and here you can represent this as a benzene. So carbon-carbon bond length. If you see carbon-carbon bond length, in this case, carbon-carbon bond length is 154 picometer. Here, this carbon-carbon bond is, 134 picometer. And this bond lies between carbon-carbon double bond and single bond, and comes out to be, 140 picometer. So as per carbon-carbon bond of benzene is concerned, it is lies between somewhere between single bond and double bond, and you can see it is something very similar to that of 1.5 bond. Now, apart in the case of benzene, if we see another example of resonance and resonance hybrid structure, This may be, let's say, ozone. In the structure of ozone O3, it's one of the resonating structure of ozone may be, let's say, this oxygen having positive charge, this oxygen having negative charge, and lone pair of electron and one lone pair of electron present on this oxygen atom. It's another resonating structure may be, let's say, this bond can break in this direction, and it is O and double bond O here, having only two lone pair of electron having positive charge here, and lone pair with negative charge. The hybrid structure of ozone may be, it is oxygen and oxygen here, and having pi bond character. Effectively, it is nothing but resonance hybrid structure. Resonance hybrid structure of ozone. And again, in the case of ozone, no bond is exactly single bond, no bond is exactly double bond. It is somewhere lies between single bond as well as double bond. So as per ozone is concerned, it can show properties of both. It can show properties of both resonating structure, carbon-carbon single bond, as well as, carbon-carbon double bond. Sorry, oxygen-oxygen single bond, as well as oxygen-oxygen double bond here. So hybrid can show properties of both the resonating structure. It can show properties of, it can show properties of first resonating structure as well as second resonating structure. So again, if you see in the case of similar compounds, one compound is O double bond O, it is O2. Another compound may be HO and OH, and another maybe you can just try to imagine, let's say, ozone hybrid structure. So in this case also, as per oxygen, bond length is concerned, it is found to be 121 picometer. It is found to be, 148 picometer, and it is found to be, 128 picometer. So as per ozone is concerned, its bond length lies between somewhere between single bond and double bond. So again, you can say its bond is somewhere between 1 and 2. So it is something very similar to, let's say, 1.5 bond. In the case of carbonate ion also, in the case of carbonate ion, CO3 2 minus, it's one of the resonating structure, maybe it is O minus, and let's say O minus having, 3 lone pair of electron here, and lone pair of electron can be donated. This pi bond can be break in this direction. Thus, it's another structure should be. It is O minus, it may be double bond O here and O minus with 3 lone pair of electron here and 2 lone pair of electron. It's another resonating structure should be. This bond can be break in this direction, and it's another structure should be. Let's say it is O double bond O, it is O minus and O minus having lone pair of electron and lone pair of electron and lone pair. So they are the 3 resonating structure of carbonate ion. its hybrid structure should be, it is oxygen, it is another oxygen and oxygen atom here, and it is going to be hybrid structure. Overall, it consists -2 charge. So in the case of carbonate ion, CO3 2 minus, carbonate ion, again CO bond length lies between single bond and double bond there. So as per resonance concern, I am repeating again, let's say molecule can have few molecule or ion may require more than one loose structure to explain all. All structures are just a structure, and the actual structure is going to be resonance hybrid. Resonance hybrid can show both resonating structure. This is just the introduction of resonance in this chapter. We'll see much detail of resonance hybrid or resonating structure in another chapter known as general organic chemistry. Further, if you move, another theory, you can say it is molecular orbital theory. It is MOT to explain bonding of the compound. So first, if you see limitation of valence bond theory, limitation of, let's say, VVT valence bond theory. In limitation of valence bond theory, according to this, if you see bond is formed due to overlapping. Bond is formed due to overlapping of half-filled valence orbital. And the meaning of half-filled valence orbital is they are the orbital of only valence shell. Valence shell means they are the orbital correspond to outermost shell of particular atom. And according to this, according to VVT, for example, if you see the structure as B2, and if let's say it is another molecule as O2, boron molecule and oxygen molecule. Boron electronic configuration is, it is 1s2, it is 2s2 and 2p1. In the case of oxygen, it is 1s2, 2s2 and 2p4. It is oxygen electronic configuration. And in the case of boron, if you see outermost shell, it is 2s and 2p. So it is 2s2 and 2p1. In the case of oxygen, it is 2s and it is 2p4. This may be representation of 2s2 and 2p4. Boron consists of one half-filled valence orbital in its valence shell, and thus according to VVT, it can form one bond with boron. In the formation of bond due to sharing of electron, this electron will also paired up. Same in the case of oxygen, as it consists two valence half-filled orbital, and thus it can form two bond with another oxygen atom. And due to sharing of electron, this electron is also paired up and this electron is also paired up. And thus, according to given theory, so according to BVT, both B2 and O2 should be, both B2 and O2 should be, diamagnetic. Here all electrons are paired up. So if you remember, the term diamagnetic means it will be repelled by external magnetic field and its all electrons should be paired up. So according to valence bond theory, both B2 and O2 should be diamagnetic. Both B2 and O2 should be diamagnetic. No electron is, unpaired here. But experimentally, B2 and O2 are found to be paramagnetic. Both B2 and O2 are found to be paramagnetic in nature. Experimentally, this can't be explained with the help of valence bond theory, and thus we need another theory here. We need another theory known as, molecular orbital theory. According to MOT, according to molecular orbital theory, every covalent bond is formed due to, according to molecular orbital theory, every covalent bond is formed due to linear combination of atomic orbitals. Every covalent bond is formed due to linear combination of atomic orbitals. So you can say is LCAO. Another point related to MOT is due to, it is atomic orbitals of, you can say, of, inner shell as well as, valence shell, which is outermost shell. So if you see, one of the basic difference between valence bond theory and molecular orbital theory is, according to valence bond theory, only valence shell orbital participate in bonding. In the case of MOT, it is valence shell as well as inner shell can participate in bonding. Further, due to linear combination of atomic orbital, due to linear combination of atomic orbitals, you can say due to linear combination. Due to linear combination of two atomic orbitals. Due to linear combination of two atomic orbitals, two molecular orbitals will be formed of different energy. Due to linear combination of two atomic orbitals, two molecular orbitals will be formed of different energies, whichever consist less energy is known as bonding molecular orbital, and higher energy orbital is known as anti-bonding. Due to linear combination of two atomic orbitals, two molecular orbitals will be formed of different energy. Whichever consists less energy is known as bonding molecular orbital, and higher energy orbital is known as anti-bonding molecular orbital. So it is something very similar to that of hybridization, which is the concept of intermixing of atomic orbital to form new set of orbitals known as molecular orbital. So due to linear combination of two atomic orbitals, two molecular orbital will be formed of different energy. Whichever consists higher energy, it is known as anti-bonding molecular orbital, and low energy orbital is known as bonding molecular orbital. For example, due to linear combination of two 1s orbitals, due to linear combination of two 1s orbitals, two molecular orbital will be formed of different energies. One may be represented as, let's say, sigma 1s, and another may be represented as sigma star 1s. With sigma represent, according to valence bond theory, s orbital can form only sigma bond. So sigma 1s may be it is bonding molecular orbital, and sigma star 1s it is anti-bonding molecular orbital. Anti-bonding molecular orbital consists relatively higher energy. If you see a pictorial representation of, let's say, energy of orbitals and linear combination, for example, for linear combination of two 1s orbitals, on this axis, let's say if we take energy, on this axis, let's say if we take energy here, this dibba, this box may represent, let's say, 1s orbital. This may be, let's say, 1s orbital here. You can simply say here you can represent certain atomic orbital. It is another atomic orbital, and somewhere in middle it is going to be, let's say, molecular orbital. Due to linear combination of 1s and 1s, we have formation of, molecular orbital, and it is another molecular orbital is formed. In the case of 1s and 1s, due to their linear combination, two molecular orbital will formed. One, it is sigma 1s, and another orbital may be, let's say, sigma star 1s. So 1s and 1s, due to their linear combination, we have sigma 1s and we have sigma star 1s. Due to linear combination of these two atomic orbitals, molecular orbitals will be formed, which is sigma 1s and sigma star 1s. Further, sigma 1s is, bonding molecular orbital, and sigma star 1s is anti-bonding molecular orbital. So it is, bonding molecular orbital, and it is anti-bonding molecular orbital, ABMO and BMO. In this case, according to molecular orbital theory, the strength of bond is measured in terms of strength of bond is measured in terms of bond order, where bond order may be, let's say, half of NB minus NA, where NB is number of electrons present. Number of electron present in bonding molecular orbital, and Na is number present in anti-bonding molecular orbital. So strength of bond is measured in terms of bond order, where bond order is nothing but, let's say, half of Nb minus Na, where Nb is number of electron present in bonding molecular orbital, and Na is number of electron present in anti-bonding molecular orbital. So if you see bond strength, or bond energy is directly proportional to bond order. Bond strength or bond energy is directly proportional to bond order, and bond length is inversely proportional to bond order. Bond length is inversely proportional to bond order. No, for example, for H2 molecule, for H2, in the case of H2 molecule, H2 molecule will form due to linear combination of atomic orbital of hydrogen. So on this axis, if energy is given, and it is 1s orbital, and it is another 1s orbital. So due to linear combination of 1s and 1s, two orbitals will be formed. One may be, let's say, sigma 1s, and another orbital here. Another orbital here, you can say it is sigma star 1s. This may be correspond to, hydrogen atom. It is same as, correspond to hydrogen atom. And it is for, H2 molecule. In this case, 1s has, let's say, 1 electron and 1 electron each in the case of hydrogen atom. Due to linear combination of hydrogen atom, let's say H2 molecule can form, and in which we have, let's say, sigma 1s and sigma star 1s bonding molecular orbital and anti-bonding molecular orbital. So total it consists, let's say, 1 electron and 1 electron each, and total it consists, let's say, 2 electrons here. Now these 2 electrons can present, let's say, somewhere like this in sigma 1s, and 0 electron present in, sigma star 1s. So overall electronic configuration of H2 is concerned. It is sigma 1s2, sigma star 1s0. So no electron present in technically, sigma 1s, sigma star 1s. So electron present in bonding MO. Electron present in bonding MO is 2. Number of electron present anti-bonding MO is 0. Its, bond order should be half of NB minus NA, and it comes out to be, half of 2 minus 0, comes out to be 1 as a bond order, as no electron is unpaired in the case of H2 molecule, and thus it is found to be, diamagnetic. Same in the case of, let's say, H2 plus. H2 plus is sigma 1s1, sigma star 1s0. Here number of electron present in bonding is 1. Number of electron present in anti-bonding is 0. Its bond order should be half of 1 minus 0, and it will be half. And it is paramagnetic. Similarly, in the case of, let's say, H2 minus, it is sigma 1s2, and it is sigma star 1s1. In this case, number of electron present in bonding is, 2. Number of electron present in anti-bonding is 1. Its bond order should be half of 2 minus 1 as half. And it is also found to be, paramagnetic. So in the case of H2 molecule, H2 is found to be diamagnetic. In the case of H2 plus, it is found to be paramagnetic. And in the case of H2 minus also, it is also found to be paramagnetic in nature. So I hope you have noted down this. Okay, so to move further, for B2 molecule boron, if you see this energy diagram here, on this axis, let's say we have energy. These are some atomic orbitals here. So this orbital may be, 1s and 1s. Due to linear combination of 1s and 1s, two molecular orbital will be formed. One is sigma 1s, another orbital may be, sigma star 1s. It is 2s and let's say 2s, and due to their linear combination, two molecular orbital will be formed. Similarly, in the case of, let's say, B2, due to linear combination of 1s, two molecular orbital will be formed, may be represented as this. In the case of 2s, again, two molecular orbital will be formed as this. In the case of, 2p orbitals, we have 2px, 2py, and 2pz. So this may be 2p and 2p involve all three, 2px, 2py, and 2pz. So due to linear combination of these two orbitals, two molecular orbital will be formed, and this may be another molecular orbital here. Same anti-bonding molecular orbital will be formed, and bonding MO is also formed as this. Here, as per name of these orbitals is concerned, it may be sigma 2s, and this may be, let's say, sigma star 2s. It is, sigma 2px, it is pi 2py, pi 2pz. It is, sigma star 2px, it is pi star 2py, and it is pi star 2pz. Here, overall, as per B2 is concerned, B2 boron consists, let's say, 2 electron in 1s and 1s, and 2 electron in 2s and 2s. And one more electron present in, let's say, 2p and 2p here. So due to linear combination of, let's say, 1s and 1s orbital, 4 electron overall. So these 2 electron present here and these 2 electron present here. These 2 electron and these 2 electron present here. Due to linear combination of these two orbital, here we should have 1 electron and one electron unpaired each in, let's say, two different orbitals, which may be written as, let's say, pi 2p y and pi 2p z orbitals. This may be, let's say, for boron as a atom, and this may be for B2 molecule. Now, if we have to write down the electronic configuration of B2 as a molecule, it consists two electron in, sigma 1s. It consists two electron in sigma star 1s. It consists two electron in sigma 2s. It consists two electron in sigma star 2s. And it may be, let's say, pi 2py1, and it may be pi 2pz1. So these two electrons present in, let's say, pi orbital, 2py and 2pz. So this may be the electronic configuration of, let's say, B2. As per number of electron in bonding MO is concerned, it is 2, 2, and 2, 6. Number of electron present in anti-bonding MO is concerned, it is 4. And its, bond order should be half of 6 minus 4 as 1 as a bond order. So its bond order is nothing but, let's say, half of 6 minus 4, 1 as a bond order. As per B2 is concerned, it is found to be, paramagnetic. As per B2 is concerned, it is found to be paramagnetic in nature, as it has two unpaired electrons and its magnetic moment. Total, it is, let's say, two unpaired electrons. So it is root of 2 into 2 plus 2 comes out to be root 8 Bohr magneton, and it is, let's say, 2 root 2 Bohr's magneton. As per magnetic moment is concerned. So according to, valence bond theory, this is going to be, this is going to be diamagnetic, and according to molecular orbital theory, it is going to be paramagnetic in nature. Now, apart from B2, if you have to see for, O2, oxygen. So for O2 molecules, for O2 molecules, on this axis, let's say if we have energy, on this axis, let's say if we have energy, this may be, let's say, sigma 1s and sigma 1s. Due to their linear combination, it is sigma 1s and sigma star 1s. It is sigma 2s, and due to their linear combination, same. Let's say, it is 2px, 2py, and 2pz. In the case of oxygen, here it may be, oxygen atom. This may be O2 molecule, and again, let's say this may be oxygen atom here. Due to linear combination of oxygen and oxygen atom, so is another combination possible here. And similarly, another one. So in the case of oxygen, it is, let's say, 2 electrons present here and another 2 electron. One s2 and 2s2. So this orbital is going to be, 1s, and it is 1s, it is 1s orbital and 1s orbital. This orbital is going to be, sigma 1s, sigma star 1s, it is sigma 2s, and sigma star 2s. This orbital may be sigma 2px. This is, pi 2py and pi 2pz. This orbital is nothing but, let's say, 2p and 2p. This orbital is nothing but, pi star 2py and pi star 2pz. And this orbital is nothing but, let's say, sigma star 2px. So in the case of oxygen, this is the electronic configuration of oxygen. In the case of oxygen, this is the electronic configuration here. And overall, O2 consists 2 electron in sigma 1s, 2 electron in sigma star 1s, 2 electron in sigma 2s, 2 electron in sigma star 2s, another 2 electron, and another 2 electrons. So till now we have filled 14 electrons in O2. So this may be 15th electron and this may be 16th electron. So as per electronic configuration of O2 is concerned, it may be electron present in sigma 1s2, it is sigma star 1s2, it is sigma and sigma star 2s2. It may be sigma 2px and it is pi 2 pi 2 and it is pi 2pz2. Further, it is pi star 2py and it is pi star 2pz1 and 1. So overall total number of electron present in bonding MO is 2, 2, 2, and let's say 2. So overall it consists 10 electron present in bonding MO. Total number of electron present in anti-bonding MO is found to be 6. Its bond order is nothing but half of 10 minus 6 and comes out to be 2. So as per bond order is concerned, it is half of 10 minus 6. The bond order comes out to be 2 here. As per O2 is concerned, it has 2 unpaired electrons, and thus O2 is found to be, paramagnetic. O2 is found to be paramagnetic. Overall, its magnetic moment is, as we have 2 unpaired electrons, so it is root of n into n plus 2. So it is 2 plus 2 comes out to be root 8, and Bohr magnet. So the magnetic moment of O2 is found to be root 8 Bohr magneton. O2 is found to be, paramagnetic in nature. So overall, if you see, although molecular orbital theory is superior theory in comparison to valence bond theory, but mostly, 80 to 90% part of, chemistry of 11th and 12th is explained with the help of valence bond theory only. It has certain limitation related to, magnetic properties of molecules, which can be further explained with the help of MOT, molecular orbital theory. So according to valence bond theory, both B2 and O2 was found to be, diamagnetic, but according to molecular orbital theory, it will be paramagnetic in nature. So as per O2 is concerned, its bond order is found to be 2. So in the next lecture, we'll continue with chemical bonding. So that's all from our side for today's lecture.